So we have been looking at Lewis structures and how we can start to take different atoms, covalently bond them together to make these covalent molecules. And then from those molecules, we've actually been able to determine in three-dimensional space how those atoms range themselves around this central atom. And so given what we know about our atoms and how they start to repel, we can start to get these shapes. And now from these shapes, we can actually look at kind of that next stage or that next piece of the picture, and that is our bond molecularity in terms of our polarities, our molecule polarities, whether or not the molecule is or is not polar. Now it's going to depend upon how we draw our structures and how we start to look at our three-dimensional space as to whether or not a molecule may or may not be polar and how that then affects its individual properties. So by way of review, remember your steps for drawing our Lewis structures. Let's start with the chlorine. If we got 2 chlorines, each one's got 7 valence electrons times 2 because there's 2 of them. It's a total of 14 electrons. We'll pick a central atom. I'm going to put a chlorine in the middle, bond it to another chlorine. I just use 2 electrons. I'm down to 12. I'm going to fill up all my chlorines. I'll make my dots nice and big so you can see my pairs here. I just used 12 more dots. I am out of dots. Now, good news, everybody's full. If we had to describe the shape here, we would say it is linear. We got 2 atoms straight across. As a result, we've got a nice linear molecule. Now, if we were to look at this molecule and ask ourselves, which one is more electronegative? Well, this chlorine versus this chlorine, well, they have the same electronegativities. As we go up and towards fluorine, we know our electronegativity gets larger. We could use the Linus-Pauling scale if we wanted to, but we don't need to. We know that they're identical nonmetals, and as a result, their electronegativities are the same. And so this is a nonpolar bond. Well, if the bond is nonpolar, the molecule would also be nonpolar. They're going to share evenly. So there's no weird distribution of charges as we look at this molecule. If one of these was different, say one of these chlorines was instead, I don't know, a hydrogen, well, now we've got a polar bond, and as a result, our molecule actually becomes polar as well. We'll talk more about that here in just a second, but something to think about as we're thinking about just what that means for our bond as opposed to then our molecule as a whole. All right, water. Okay, we've seen this one before. Each hydrogen's got 1 valence electron. We've got 2 hydrogens in there. Oxygen's got 6 for a total of 8. Oxygen in the middle. We join to our hydrogen. And we've got our bent molecule or bent arrangement. Some of you are fairly familiar with this when we look at kind of our biological processes. Super important that water is bent. Lots of reasons why that matters, but if you drew it straight across, sometimes they will do that. That's really just an orientation thing, right? Oh, it looks like a straight line, it's straight across. Well, no, we just rotated the molecule a little bit. And so I drew it here to try to help us see that. If we're thinking about kind of our bond angles here, linear, straight across, 180 degrees, cool. But for our bent molecule, remember that our bent molecule water falls under the tetrahedral family. Tetra meaning 4. I had this question come up a couple of times as we're working through that PhET. When we're looking at domains, our electron domains, we're looking at all the regions where there's electrons. That would be the bonds and the lone pairs. And so for our water here, we've got 2 domains that are bonding domains. And then not shown here are the lone pairs. There'd be 2 kind of up and above, in front of, and behind our water molecule. So there's 4 domains, 2 bonds, and 2 sets of, in this case, lone pairs. We can't see them in the model, but we can see them in our structure. Because these electron lone pairs actually create more repulsion, it squeezes our hydrogens together a little bit. The bond angle here ends up being a little less than 109.5, but we got this real nice bent molecule. The reason why this is important is because now we can think about how that affects the molecule. We know that oxygen, hydrogen, different electronegativities. If we think about who's closer to fluorine, that's going to be our oxygen. As a result, these electrons get pulled towards the oxygen, making the hydrogens a little bit positive and making our oxygen a little bit negative. A little squiggle here is lowercase delta. It means a partial charge. It's not a full charge. We're still sharing the electrons. We're just pulling them a little bit closer to the oxygen. Now, if we're thinking about our molecule now, we know the bonds are polar. What about the molecule as a whole? Is there one side of the molecule that is more positive and another side of the molecule that's more negative? And that's going to depend not only on the bonds, but also the arrangement of said bonds. If we're thinking just about the molecule as a whole here, we might notice that, oh yeah, this whole bottom side is positive, this whole top side is negative, and so we can actually say that we would have a molecular dipole as well. And so there's kind of 2 requirements when we're trying to decide whether or not a molecule is going to be polar. First and foremost, you got to have polar bonds. You got to have uneven sharing within the covalent bonds in your molecule. And then the second requirement you need is an unsymmetrical or non-symmetrical molecule, one that is unevenly distributed those bonds around the central atom. And so to kind of highlight that, we can kind of do what we call the fold test or the paper test. We're looking for symmetry. If we look at our water molecule here, we could fold it along this middle axis. If we were to fold the molecule on itself, these two hydrogens would line up. And so if we think about the x-axis, our x-axis has symmetry. We could fold it and these two would line up. Our x vectors, if you're in physics, would cancel. But if we were to fold it across the middle of our oxygen, if we were to kind of cut the oxygen in half, a molecule in half, and fold it that way, well, there's nothing to balance it out. We don't have any symmetry from top to bottom. And so our molecule here is polar. And we know this to be super important. This is why plants are able to pull water up out of the ground. It's called capillary action or capillary action, depending on who you talk to. And so there's a lot of reasons why these properties become important. More on that here in just a second. If we're to look at another one of our tetrahedral molecules, family molecules, we've got our trigonal pyramidal. This would be ammonia. There's two lone pairs that we can't see here on top. Let me just draw it real quick. So trigonal pyramidal. And so if we were to try to fold this, ain't gonna work. Because the lone pairs up here on top, there's nothing to counteract kind of the top side of here. And so we would say that this is also gonna be a polar molecule. It's non-symmetrical. Yeah, all the hydrogens kind of line up with each other, but there's nothing across on the other side of the molecule to counteract that. If we were to go back and look at some more examples here, give you one that's non-polar. Carbon dioxide, sorry, spoilers. Carbon dioxide, carbon's got 4 valence. Each oxygen's got 6 times 2 for a total of 12. Looks like we're dealing with 16 electrons total. Carbon in the middle. Bond to our oxygens. We just use 2 4 electrons. 16 minus 4 down to 12. I'm going to fill up my oxygens here. So my next step, fill up our outer atoms. I used 6 and 6 for a total of 12. I am out of dots. All right, well, if we're looking, our oxygens are good. They got 8 and 8, including the bonds, but our carbon's not. It's only got 2 and 4. If you remember, this is an example we saw in one of our previous handouts. We would take 2 of our electrons, bring them down, do a double bond. 2 of our electrons, bring them down, do a double bond. We now have kind of an even 8 around our carbon. Think about electronegativities. So now the question is this molecule polar? Well, who's more electronegative, carbon or oxygen? Close to fluorine, oxygen. So our oxygens are going to pull out towards the outer edge. As a result, the oxygen ends become a little negative. Our carbon becomes a little positive. Now let me ask this question, left to right, which one is more negative than the other? They're the same. As a result, there's no one side of this molecule that's more positive or negative, and we've said this molecule is nonpolar. If we want to go back to that symmetry test, if we were to fold it right here in the middle, our oxygens would line up. If we were to fold it right across the central axis, our molecule would line up. This is a symmetrical molecule. As a result, this CO2 is a gas. And when we start to look at some of its properties, it's related back to this nonpolar arrangement of our carbons and oxygens. Cool, a couple more examples for us to start to look at. We've got our boron trifluoride. College board loves this one because of how weird this one is. We're talking about, you're not going to like it in particular, but we're talking about boron's got 3 valence electrons. Each fluorine's got 7 times 3 is 21. We've got 24 electrons total. I'm going to put my boron in the middle. I'm going to attach my fluorides. I just used 3 bonds, which is 6 total. We're down to 18 electrons. Fill up my fluorines. And I think I've used them all. I use 6, 12, 18. I am out of dots. And the reason why AP board likes this one so much is technically everybody's stable. But wait! I hear you cry. Boron doesn't have 8 valence electrons. Oh, this goes back to how we can start to become stable and when we start to kind of blend our bonding types here a little bit. Who's more electronegative? Boron or fluorine? Fluorine, we know, to be way electronegative, and so it's going to pull its electrons all towards itself. Let me ask this question. Which fluorine then is going to be more partially negative? Well, none, you say. They're all going to be the same. As a result, I apologize, I ran out of halogen, so I'm stealing some of our hydrogens. Bonding amounts are the same for them. If we're thinking about kind of our outer atom here, which one's most negative? Well, they're all going to be the same. If you're thinking about your shape, we've got a triangle that is flat because there's no lone pairs on that central atom. This will be trigonal planar, 120 degrees from atom to atom around the outside here. Nonpolar molecule is very much symmetrical. If I were to cut it in half this way, these would line up. If I were to cut it in half this way, these would line up. If I were to cut it just through kind of that central axis, they would all line up with one another. So this is a symmetrical molecule. Now, if I were to change this, if I were to swap out one of these for a different atom, well, now you're no longer symmetrical. Now it's unsymmetrical. This would now become a polar molecule because we do not have symmetry all the way around the outside. Cool. Yeah, methane, we've seen this one before. Carbon's got 4, each hydrogen's got 1 for a total of 4. That's 8. I think this one's going to fall in pretty quickly. It's going to be a tetrahedral molecule. If you were using your digit dashes and wedges, maybe something like that. Sure, why not? Depending on the orientation that you've got it. Although, I think I would have something that looks, well, I did that wrong. Technically, this should have been back over here. Apologize. Been a while since I used my dashes and wedges. Very much an organic chemistry thing. All right, cool. So we got these 2 hydrogens in the plane of the board. My board's right here. We got 1 hydrogen out in front, another hydrogen out behind. Now, if I were to ask you symmetrical or unsymmetrical, you would say very much symmetrical. I've got even hydrogens all counteracting. This was a non-polar molecule. If we were to kind of think about it in 2D space, it becomes even easier to see. Got this carbon here in the middle. We got our hydrogens all the way around. No one side is going to be different than the other. This is a non-polar molecule. Again, if one of these was different, say this was, I don't know, a chlorine, now it's polar. We've got uneven distribution. We've got a non-symmetrical molecule. Now we've got a polar arrangement. Cool. As we keep looking, bond angles, tetrahedral, 109.5 between those outer atoms. Sorry, worth reviewing as we're kind of talking through our different molecule shapes. Ooh, time to get out the cleaner. Cool, want to look at a couple of the newer ones that you may or may not have seen yet. Well, I know you've all seen them, but worth mentioning, we haven't talked about them in great depth or detail. If we're thinking about an atom that's joined to 5 different domains, this would be our trigonal bipyramidal. So there's a pyramid on top, pyramid on bottom. You've got 90 degrees from this one to the center line. If we're looking at the ones around the center, we've got 120 going around the center. Turns out this one's pretty specific as to how we start to lose our atoms. If we were just to look at this molecule, if we're thinking about our kind of geometric shape, this is going to be, as I've got it here, this is going to be non-polar because I've got even distribution all the way around the outside. If I were to lose one of these, I'm going to leave kind of the bond to represent our lone pair. So 2 electrons, but not technically bonded to anyone. Cool. If we were to think about our shape now, it is our seesaw. If we're thinking about our geometry here and whether or not we've got symmetry, we could cut it here and it would fold on itself, or it's easier to see, cut it here, fold it on itself. These 2 match up, these 2 match up. Problem is up top here. If I were to cut it this way, kind of horizontally, there's nothing to match these up above that central atom. So this now becomes polar, excuse me. If I were to take away and have 3 bonding domains, 2 non-bonding domains, if we look just at our kind of molecular geometry, we've got T-shaped. This would also be polar molecule because we've got symmetry here, but not through kind of our horizontal axis. There's nothing above to balance out this atom down below. If we were to lose kind of our third one, we now have 3 lone pairs around the central atom. We've got these 2 on the outside. This is now a linear molecule, but is still symmetrical. So this is going to be a non-polar molecule. If one of these was a different atom, well, that's non-symmetrical. This has now become a polar molecule again because we've got uneven distribution of where we're kind of pulling those electrons. We have one side that's either more positive or negative than the other. Cool. Our last kind of family to talk about, worth drawing it real quick. And the big examples are sulfur hexafluoride. Sorry, look it up. Sulfur hexafluoride. As we look at our sulfur hexafluoride, we got sulfur with 6 valence electrons, fluorine with 7 times 6, 42. We got 48 electrons total. Central atom is sulfur. We got to attach 6 to the center. Oh, there's that expanded octet again. So sulfur, because it's in the 3rd row, can have more than just 8 valence electrons because it's got the 3d orbitals available to it. As a result, it can actually have more than just 8. Don't see this very often, but they do happen. We just gonna use that to attach all our fluorines, because we know our fluorines can really only bond the once, because they already got 7 valence electrons. We just use 2, 4, 6, 8, 10, 12. Down to 36 electrons. 36, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 28, 29, 30, 31, 32, 33, 34, 35, 36. Dots. A lot of dots. Cool. This is our sulfur hexafluoride. Oh, polar bonds. Very much so. Between this sulfur and this fluoride is way more electronegative. All of these are going to get pulled in terms of their bonds dipole out towards the fluorides. All the fluorides become a little negative, the sulfur becomes a little positive. But now if I were to ask you on this lovely Christmas tree molecule, which fluoride is most negative? We have an even distribution of that negative field. This is still a non-polar molecule. Bonds are polar, molecule is not. If we were to lose one of those outer atoms and just have a lone pair here on the bottom, we now have, we've got a square, right? Square going across the bottom here. And then a point on top. Our molecular geometry here would be square pyramidal. If we were to lose a second of our bonds, we now have square, because we're square around the center, square planar, because they're in a flat orientation. Would still be, this would be, symmetrical. So this is nonpolar. If you had one of those on there, so our square pyramidal, this is going to now be polar because there's nothing to counteract kind of this lone atom on top. It's not symmetrical top to bottom here. It is side to side, just not top to bottom. Cool. So when you're thinking about polar molecules, you need 2 things. Again, you got to have polar bonds and you got to have a non-symmetrical molecule. And I hear you, I can hear you. I can hear you think it. I know that's weird. The why, right? Hopefully you're always asking yourself this. Why? Why should we care? The reason why we care is that we can actually then, with high fidelity, go from this structure. What we kind of think happens with this theory of how these atoms are joined together, and then use that to explain the properties we see on the macroscopic scale. So here's what we've got. We've got a polar molecule, probably one of the most well-known ones. So this would be our dihydrogen monoxide, aka water. So here's our polar water. Polar water. To that, we're going to add a non-polar substance. A non-polar substance, in this instance, this is our our vegetable oil. I almost said corn syrup. Those are very much both polar. We've got our vegetable oil here, and you will notice very quickly, you've probably seen this before, that we've got an miscible surface, or a miscible species. We've got 2 things that are not mixing. Oftentimes in chemistry, you'll hear the term likes dissolve likes. This is why our molecular polarities are so important, because our bottom one here is polar, and our top one is nonpolar. These 2 do not mix. I'm going to add a 3rd one here. I'm going to try to go slow, see if I can get a good layer to go here. You'll have to bear with me as I juggle a couple different things all at once. So I'm just going to go ahead and slowly add. Whoop, not working here. So there's a couple good ones. See if I can get a good camera angle here. So you'll notice I've got kind of some suspensions in there. So I'm adding an additional polar substance. And what you'll notice is that it is not mixing with the oil. I'm trying to get good kind of another layer here. I think my surface tension is too high because I put the water in first. Let me see if I can get, no, not gonna work. But here's what you will notice is that it does mix. You can see it already starting to mix. Our 2 polar substances, they will mix our two nonpolar, or our polar, nonpolar will not. And so I added an additional polar substance. It did mix with the polar water. I had nonpolar vegetable oil on top. It did not mix there. And so we cared pretty considerably about our molecular polarity because it affects so many of the properties as our different substances start to interact. Cool. We're going to be looking at a bunch of examples on these. If you got questions, give us a holler.